In a single crystal X-ray diffraction experiment, a crystal is placed in the center of the instrument. The crystal is constantly rotated in a beam of X-rays, and a two-dimensional detector records the signals from the sample. From the position and the intensity of these signals, the three-dimensional structure of the sample can be unambiguously determined. Many minerals such as diamond and salt, organic molecules such as sugar, and drugs such as salicylic acid appear as small crystals. In these crystals, atoms, ions, or molecules are arranged in a highly ordered structure, forming a crystal lattice that extends in all three dimensions. This crystal lattice acts as a diffraction grating for X-rays. It is at this scale that the story of single crystal X-ray diffraction begins. X-rays are high-energy light with a repeating period called a wavelength, or lambda. Since the wavelength of X-ray light is similar to the distance between atoms in a crystal, X-ray diffraction can be used to determine the distance between atoms in the crystal. To understand X-ray diffraction, we first have to look into wave properties, called interference. Very similar to throwing two rocks into the water, the circular ripples that result from the two stones seem to pass through one another as they propagate out from where the stones entered. This is known as interference. If the waves are in alignment, the signal is amplified. This is called constructive interference. If the waves are out of alignment, the signal is destroyed. This is called destructive interference. When an X-ray encounters an atom, its energy is absorbed by the atom's electrons. Electrons occupy special energy states around an atom. Since the absorbed energy is not large enough to release the electron, the energy must be re-emitted in the form of a new X-ray with the same energy as the original. This process is called elastic scattering. In a crystal, the repeating arrangement of atoms, ions, or molecules forms a lattice with well-defined repeating distances. When planes in these lattices are exposed to an X-ray beam, X-rays are scattered by this regular arrangement. Strong amplification of the emitted signal occurs at very specific angles where the scattered waves constructively interfere. This effect is called diffraction. The angle between the incident and scattered beams is called 2 theta. For constructive interference to occur, the scattered waves must be in alignment, meaning the second wave must travel a whole number of wavelengths. In this case, 1/2 of a wavelength is traveled on the incident side, and 1/2 of a wavelength is traveled on the scattered side, resulting in 1 additional wavelength. In the case of the next X-ray, 1 wavelength is traveled on both the incident and the scattered sides, resulting in 2 wavelengths. This reinforcement occurs throughout the crystal. The exact angle at which diffraction occurs can be determined from the red triangle. The angle at the top is theta, half the angle between the incident and scattered beams. The long side is the distance between the atomic planes, and the short side is 1/2 of a wavelength. The relationship between the diffraction angle and the spacing between the atoms can be determined by applying the sine function. Rearranging this equation yields an equation commonly known as Bragg's law, named after Sir William Henry and William Lawrence Bragg, the father-son team who won the Nobel Prize in 1915 for their work analyzing crystal structures with X-ray diffraction. Today, the technique of single crystal X-ray diffraction is used to determine the three-dimensional structure from a wide variety of crystals. Single crystal X-ray diffraction helps scientists to identify the products resulting from chemical reactions and to understand the mechanisms behind these reactions. Single crystal X-ray diffraction is also applied to determine the structure of proteins, which play a key role in all organisms, including humans. For example, our ability to see light depends on a protein called rhodopsin, located in the retina of our eye. Single crystal X-ray diffraction helps to understand the mechanisms behind seeing. Similarly, the detailed knowledge of protein structures is essential to develop new, life-saving pharmaceuticals. Single crystal X-ray diffraction provides important information to finally understand the interaction of new drug candidates with the proteins in our body. As scientists push their ability to engineer materials on the atomic level, single crystal X-ray diffraction becomes an increasingly important tool in their toolbox. Advances in equipment design have made single crystal X-ray diffraction easier to use and more powerful than ever.